what's going on here is that what do we know about y equals e to the x? Why is it so prominent in the curriculum for stage 6? Why is it there so much? What's the big deal? Who cares? But it turns up again and again and again and again. Well, on one level we could talk about the science of the practical use of e to the x, which is what you guys do at school, or we could just think about the pragmatic relationship that it has with another function. So if I take y equals x, up there like that, y equals x, and I do a reflection in y equals x, what will I get? So the idea here in class, what I do is I get my senior students to ink this up, get a little piece of paper, give them a little paper square, ink it up, and then fold down the crease, fold the crease over. There's me folding the crease, rub-a-dub-dub-dub-dub. Right, and then what you'll get from your inked up sheet, you can use a reflector if you've got one, if your school's given you one, but if you don't, you can just do the rub-a-dub-dub, and what you get is this. Now what is this? This is my question to you. What is this? Okay, what is this? Remember, this is a concept. What is this? What have I drawn? There's a concept of what I've drawn. Anything reflected in y equals x is what? So the power of y equals x is raising its ugly head again. Anything reflected in y equals x is what? It is a?
Well, it's a logarithm.
Yep. But the reflection is an inverse. And the word that we associate with inverse is? Undo. What's the undo of differentiation?
Integration.
That's absolutely right. So the undo of y equals e to the x was pointed out, is the ln of x. Okay, so these two guys are related. They're related as inverses of one another. So how does that work? Now, if you get the definition of an inverse, where the power is raised to the base of the number, and so it goes on, your students will be very confused by that if they get that in Year 10. I feel as though this is a better approach in that it's a bit more pragmatic for students. So let's use the undo nature of it. Alright, so if we've got, now the ln here is the natural logarithm, base e. So y equals e to the x. What's the operator on x? That's a funny way of saying the function, but a function can be an operator. The operator is exponential. So that's the phrasing, the operator is exponential. How do we undo exponential? Remember, this is for teachers, right? You can teach students, but this is for you guys. How do we undo exponential? Okay. Now this is often touted as an elite idea in stage 6, but it's really not. So we take the ln of both sides. What's the significance of this? The significance of this is ln next to e is undo. So the ln of y is equal to x. Now, for whatever reason, and I think it's to do with the definition that you get in Year 10, that message isn't coming out of high school. Okay? Let's try it again. Let's try y equals the ln of x. What's the operator on x? It's the logarithm function. So how do we undo that? So we're going to raise both sides e to the ln. And what do you recognise there? This is undo. So we managed to isolate the x. In many ways, apart from exact values trig, that's the most important thing you'll learn about teaching maths in a high school. Because it's if it's not obvious to you what's going on, it's a loss. So to take that, and I think I did an example of a separation of variables DE, and I showed you how that applies. But let's try something else. Y equals 7 to the power x. What's the operator on the x? Exponential 7, isn't it? So in order to get this out, we can take the base of 7. Now, as soon as I start talking like that, you're going to switch off and you're going to think, oh my God, what's he talking about? So let's not do that. Let's say, how do we undo the exponential? What did we do when we undid 2.73 ... infinite to the power of x? We took the log, didn't we? We took the log base e. That's how we undid it. So what do we think we'll do? Remember that e is a number, 2.7. So if the number's 7, what do we think we're going to do? We're going to take log base 7. That's going to be our undo. So if we take the log base 7 to both sides, what's going to happen? Really? What's that? Undo. So it works with any log. Okay? It works with any log. You can take this mechanism of raising powers and taking logs. You've just got to match the log. If you can match the log, you can undo it and isolate it. What about y equals the log of base 7? How do we undo? How do we undo log base 7? We take the exponential. So we raise y to the power 7. We raise log base 7 to the power 7. And then what happens? This is the opposite, isn't it? This is undo, gone. So on our final part, we've managed to find it. So it's very uncomfortable the first time you meet this. And the explanations that are in the text don't go a long way to supporting you. I think the one I'm talking about is probably New Century. Stage 5, New Century. Look up logs. Take a couple of Panadol before you do it. Because you won't come away thinking like this. You'll come away thinking, how the hell am I going to teach these kids logs and indices? And it's really straightforward. E and ln are exponentials. I should say logs and exponentials, shouldn't I? Logs and exponentials are inverses, and they undo, and all you've got to do is match them. So the power of this is quite significant. I know that you're thinking about how that permeates its way all the way through the syllabus. Now, who wants to give me an example? Who wants me to do an example for them? You pick it. I don't know. Y equals. What are we doing? We're either doing a log or an exponential of some number. Someone give me an example. Something to the power x, or log base something x.
Often, for example, in chemical reactions, you could have an exponential, something that's exponentially reducing. So e to the, for example, minus 0.7x.
Okay, so it would be the same proposition, wouldn't it? Nothing changes simply because of the idea. Now, what we're going to do here is just be a little bit careful, and I'll do it on the reverse example of this, but for here we need to be a little bit careful. For example, if this were 2e, that would be a problem. Okay, because we couldn't put the ln 2e minus 0.7x. That would be a mistake. That wouldn't be undo. That's a maths idea. Okay, so we can't have, we have to do other work. We divide by, throughout, or what have you. We have to isolate the expression of e in order for this to work. So if y is equal to e to some other thing, and this happens in finance and the like, we can still take the ln of both sides, and because there's nothing interfering, we treat this like a box. That's really what you're saying. So e to the minus 0.7x, because the undo is between ln and e. So for here, we take the ln of y, or the ln of y, and we would take the ln of e to the box, and we would get the ln of y is equal to the box. Here, the ln of y is going to be equal to minus 0.7x. Okay. So in that case there, very straightforward. Now you can check that with your technology. All this stuff works with your technology. Okay, so you can put in 7 to the power y equals x, or y equals log 7x, and tell Mathematica to solve for x, and it'll do this for you if you want to check it. Okay, so let's do the opposite. Let's do y equals the ln of 0.7x. Now, is this going to be a problem? No, I don't think it is, because all we're going to be doing is using the exponent. So we'll have e to the y is equal to e to the ln minus 0.7x, and so we've got undo. So e to the y equals minus 0.7x. So where the log laws come in, sometimes you'll strike an example using your log laws, where now we're talking really about log laws rather than we are about e and ln. But so what they like to do at uni here is they like to say, so an example of a log law is that log AB is equal to log A plus log B. And so what they'll do is they'll put the question together, or A to the power X, or P to some power P, and then that's P log A. So what students will do is students will get it in this form. So the question will be like 10 log X. Okay, now if you raise that to the E, expecting to undo, let me just change that to ln, rather than change it, I'll just dot it. Y equals 10 ln x. So what if you were to do this, that would be incorrect. You can't do undo there. That's not an undo. So this is incorrect. But what we can do using the log laws, before we raise it to the power, is that we can rewrite using log laws, using the one up the top there, and where we had 10 log x, we can write ln x to the power 10. Now that will work. So we can raise e to both sides, and we'll still get undo. So e to the y will be e. Now this often happens when you're doing algebra and you're putting together special numbers and you're trying to find what the solutions are. But anyway, this is the mechanism. This is the mechanism for that. Okay, so when you're thinking about it, get it straight and clear. Is it about log laws, or is it about e and ln? Or is it both? Because sometimes it's both, isn't it? Sometimes you'll get problems that have both. Okay, so I probably would need to dig one out, but I just won't do that at the moment unless you guys ask me to do that. So I'll say, all right, if you ask me, I'll dig one out, but I will press on otherwise. Okay. Now the thing is, what we've got is this very interesting and powerful maths idea related to inverses. Okay. So students struggle with that. They struggle with learning that anyway. Okay. So what's going on with the calculus idea? Often what a student will do is they'll see e to the x and you can see the whites of their eyes. It's like, oh my god, are you serious? And even Lynn. Okay, but this is why the maths idea is the one that needs to come across in one form or another. And then on top of that, you've got log manipulations that go on, solving questions with log manipulations. But try and separate the explanation in terms of undo from log laws and log manipulations for solving equations. All right, so what's the story with the calculus idea? Well, Leonhard Euler, and he's Euler, and I was going to mention him next week as well. It's spelt Euler, but it's Euler. Was profound, probably the most profound mathematician we've had. And 400 years ago, they had no computers. So if you think about any work that they do without computers and without these lovely pens and all of that stuff, goodness gracious me. So y equals some number raised to the power x. And a very good question was to say, well, what is the M curve? When I say M curve, what do I mean? What's another way of saying that? And why do I bother using M? What's differential calculus all about? Not allowed to tell me.
Gradient.
You're not allowed to speak. You got to do those ones. Yeah, good. That's right. 100%. You get it fully marks. Okay? You'll have a lot of fun with kids doing that. The more interactive stuff you can do, waving and stuff, is important. So M curve is the differential. So what's the differential of this? So what we could do is we could put a number in there. Now they use limit ideas. They didn't do what I'm doing here. This is not scientific at all. But I'm just going to put little linears along there for my y equals 2 to the x. And then I'm going to go and plot it. And there it's cutting through 1, so that'll be the same. And so I'm going to exaggerate it. And I'm going to kind of flatten it out. And I'm going to call it y dash is equal to some other number to the x. Not quite the same. Not quite the same. Okay. So what about if we could try y equals 3 to the x. So y equals 3 to the x would be, we would think, a little bit steeper. And I could go and do the very unscientific thing that I'm doing here with little linears. And if I did it in the limit, it would be scientific. And then I'm going to exaggerate it and say that it came out a little bit steeper. So y dash, or the M curve, was a little bit steeper. Gee, they look very close. So the question was then asked, I wonder, is there a number where I can do this curve, this testing, okay, and when I take the derivative, something miraculous happens. And what's the miracle? The miracle is that the M curve is the same curve. Now we can use partial implicit differentiation to prove this, and they attempt to do that in the Cambridge Extension 1 book, but it's a bit clumsy the way they do it. But essentially this is what happens. We get these, they're not quite the same curve. But look what happens when we do this one. Dun, 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 dun. Okay, so this is a hugely profound moment. There's a function who has this value, and it's also its derivative. I better put m of x. Okay, it's also its derivative. Now, it's the only function that does that. There's no other function. What's the derivative of x squared? 2x. What's the derivative of, or what's the integral of, what's the derivative of e to the 2x? 2e to the 2x. It's not the same curve. What's the derivative of e to the x? It's e to the x. How easy is that? You can do it in your head. So we love e to the x. So this is why there's a bit of a gap between students and this idea of, wow, we love e to the x. E to the x has got this massive thing that it can do with ln. It's an undo. But then it's also the easiest calculus that we can do. What's the integral of e to the x? If the derivative of e to the x is e to the x, the integral of e to the x has got to be? Really? You're joking me. It's e to the x. This is awesome. So the simplest calculus you can do on one level, because if you do d dx1, that's not obvious. d dx1 is what? So now I'm doing that expression type differentiation rather than an equation, y equals 1. What's the d dx of 1? In other words, what's the gradient of the number 1? The gradient of number 1, has number 1 got a graph? Yeah. We did this last week. That's the graph of 1. What's the m of that? The d dx of the number 1 is 0. Okay? So that's different. That's not straightforward. This one here, yippee, happy days. Alright, because we can always do the differential and the integral of e to the x. Now where it becomes a bit tricky, of course, is when we put it into chain rule and the like, but the fundamental idea isn't changed at all. So what happens with the ln of x? Now I think this is where the confusion comes up. I think improperly, students learn the maths idea improperly and have some inkling that e and ln are mixed together. And then when they come to calculus, they have some idea that somehow that still remains. And it's definitely not. You can clearly see there's no ln in this. Okay, calculus E is its own idea. What's the ln? What's the m curve for ln? So if I do the ln, now the ln of x is going to be this one, isn't it? And so y equals the ln of x, log base e. What's the m curve for this one? Well, I've got to go and grab, very unscientific, my little linears. Very positive, positive, getting less positive, less positive, less. That should be more curved than that. Should be flattening that out a bit. But essentially, it's the 1 on x. Hyperbola. Now clearly, they're not related. They're nothing to do with each other. Okay? They're nothing to do with each other. So it's very important that students make the clear distinction that in calculus, they're nothing to do with each other. In mathematics, they are. They're linked. They're inverses. They undo each other. In calculus, nothing to do with each other. Now you can get questions in calculus that have both ln and e in them. for whatever reason. And so that can cause confusion as well. And whether there has to be an undo and then a differential or whatever it is, that can be a cause of confusion. Okay, so one of the things that I want to just draw to your attention as you go into your careers is if we ddx the ln of x, which I just did for you, we know that that's going to be 1 over x. Okay? If we now do the next step, which seems like a perfectly natural thing to do, okay? What about if we do this? It seems like the next step, doesn't it? It seems like the next most obvious step, but it's not. Okay? Don't go into your classrooms and put that up on the board. That's a 4-unit problem. Okay? Because the ln of x is a very complicated integration. Okay? And so we need to be extremely careful about integrating the ln of x. So please, if you're going to do d dx ln of x equals 1 of x, or you're going to do your little linears and show them y, that's okay. Do that. Here I just did the integral of e to the x because it didn't matter. Okay, but it's a new teacher mistake to go in and put that up on the board and then think that you're going to continue your lesson. Okay, it doesn't work. So I'm just highlighting that for you. Please be wary. Don't put integration of the ln of x up unless you're practiced in doing the thing. So the way that we have to deal with this is a thing called integration by parts, and I'll quickly do it now so you've got it. Integration by parts you may have done, but it's an extension 2 topic. And essentially what we model is we model the number 1 in disguise. And we treat 1 as though it's a polynomial. And the polynomial, we know we can't integrate this, and so what we have is the integral of u dv is equal to uv minus the integral of v du. That's the integration by parts equation. Okay? So when we do this, look at the transition we're making. There's a lot of work there. So 1 in disguise is sitting in there dashed and hidden, and there's our 1. So because we have to integrate v, we don't want the dv. We have to integrate dv to be the ln. So what we do is we make the 1 the dv and the ln the u. So we assign those parts to get this out. This is how integration by parts work. So if you've not encountered that before or you've forgotten about it, I'm just giving you a record that you can go back over. Okay? So I'm not assessing you on this. Alright, so let's have a look. U is equal to ln of x. Now the equation calls for du. That's good because the derivative of du dx is the u dx of the ln of x is 1 over x. That's good. Okay, and in actual fact I have to isolate du and say that du is equal to 1 over x dx because I'm going to substitute everything on the right hand side for this term here. The next thing I want to look at is dv. dv is equal to the polynomial 1. This is the simplest polynomial. So if I'm going to integrate both sides, what am I going to get? So what I'll get here, if I integrate dv, I'll end up with v. And over here, v will be equal to now have I made a mistake there? No, I think everything's okay. I'm just hesitating because my v is v, which is a bit unusual. So when I come and do the integral of u to v, I've got to put it all together. So my u is the ln of x. Sorry, the variable is x. I knew I'd made an error. So I should have put over here dx. My bad. So the integral of the v will give me v, and the integral of 1 dx will give me x. So this term up here, uv, is x times ln of x minus the integral of x. Now du is 1 over x dx. Sorry about that, I should have put the dx on the back here. So x, the ln of x. Now this is the integral of 1, because x over x is 1 dx, so we're back to that. So what we're going to do is conjure an x plus c in this example. Okay, so you can see that it's a little bit more involved than just what we did for the differential of the ln of x. Okay, it's quite a bit more involved than the differential. Okay, now of course what you can do is you can use your technology. You're not really going to do that, are you, Jason? Yep, because I love technology and I love having staff that can do stuff. So we're going to call it the integral, please, of the ln of x dx, and we're going to hit the button. Now Mathematica is smart enough to know, so it's taken the x out as a constant. So it's got the brackets. So if I do this, if I take x out and put a bracket, ln of x minus 1 plus c. So that's the bit that Mathematica has done. But either form is okay. You can see that it's come that way. So please just be careful as a staff member doing your training. Don't integrate the ln of x unless you're prepared to do that. Okay? Certainly when you're doing stuff with students, it's very easy. It's like that one where I wrote up a trinomial and the trinomial had no solutions. And it's like, well, we can't factorize this. Oh, that's a hard one. And then you blither and dither and you go, oh no, or maybe I should have checked my delta first, my discriminant. So checking your discriminant, then you know that there's solutions or not. So you've got to change it, complete the square, sketch it, or just use the quadratic formula. Now, so that's one. All right, so what I thought I'd quickly do is I didn't solve a quadratic completing the square last time, and then I'll move on to exact values tree. Is that okay? Is everyone happy with that? Is there any questions about what we've done thus far? Like, I've convoluted this a little bit by throwing this integration of ln in, but it's to highlight for you what's compartmentalise it. The mathematics idea of undo is one thing. The calculus of E is awesome, differentiate or integrate, but then the calculus of ln is a bit tricky. Differential is okay, but the integral of ln is a hazard. Okay, so please be mindful of that. So I'm just going to quickly grab I'll do a minus, and then that would be 4, but I'm going to make it go down. So 4 minus 2 will be like 2. It's a square number, but it won't be right. So let's, oh no, that's not what I wanted. Yeah, I know that. Let's try that. So I'm just doing it in my head. Yeah, it's shifted it down. It's a perfect square at 2 shifted down to 2. So that's what I want. So it's x squared plus minus 4x plus 2. So here's a solution for a quadratic completing the square. I did the other ones, x squared minus 4x or plus 2. I think that's what it was. Yep. Okay, so if we're solving this, we're setting it to 0. Now we've got to go through the steps of making a perfect square, so we've got to do that coefficient thing, times it by a half, and then squaring that. And that's our square number. That goes together with our x squared 4x. We're going to add 4, so we've got our plus 2 shifter. We added 4, so we've got to subtract 4. That's your both sides. How you explain that to your students, that's entirely up to you. I could have done this. I think I went through this with you when I did it very briefly. I could have just said we'll add 4 to both sides. And that's okay to work that way if you want to do that. Okay? But equally valid is this. If I add 4, I'm going to subtract 4 to balance the left-hand side. These are the same. Okay? This is the perfect square. And I've got a shifter now of minus 2. So that's easy to draw. We can sketch that. We go to 2 because it's a minus 2, down to minus 2, and we've got this shift, and the cuts at 2, so it's going fairly steep. So we're doing a bit of curve sketching. Okay. Now, solutions please. So we're going to add 2 to both sides. We're going to take the square root. Now that'll mean we'll be taking the square root of 2 plus or minus, and that will leave us with x minus 2 equals plus or minus the square root of 2. We're going to add 2, and so the result is that we get x equals 2 plus or minus root 2. And they are the solutions here, 2 minus root 2 and 2 plus root 2. So that's all you do. You get to this point here, which is your shifter. So you can sketch this, but you keep going. Now a lot of people like to show off and do this completing the square solutions. Okay, but you've got your version now, and as always, I'm always happy if you get someone who did something and you want to have a look at it. Now, can I just ask you a question? You don't have to answer me. Are you encouraged to go and watch other staff teach? Are you allowed to just turn up at someone's class and watch what they're doing?
I've just started my second prac this week, and we are encouraged to go and reach out to other staff as long as they're agreeable.
Yeah, okay. All right, so that's something, I'm a bit of a fan of that. Some staff get a bit touchy. I mean, reverse it. What would it be like if I turned up at your class and said, I want to watch? You know, what's your motive? Why are you doing it? No. You know me, so it wouldn't be a problem, but you never know work colleagues what their issue is. But anyway, play that by ear. The more you can do to get in and watch others, the better. And the reason that I like it and the reason I'm so raw here doing the videos is because I'm not kidding myself. And you learn when I make a mistake. You see what I do. That's being human. So if you can get into the good books of someone and go and watch them make mistakes, wonderful. That's so awesome. It'll give you encouragement. It'll give you, oh, I know I would have done that too. That type of thing. All right, the next thing I'd want to move on from, unless you've got an example you want me to do, is exact values trig. All right, now exact values trig is the only thing where I ask students to do something. All right, so I ask you to get a piece of blank paper and basically do what I'm going to do here. Now, not everybody's going to be a big fan of this method. Some are going to balk at it. The syllabus teaches this in 2 stages. It teaches it in Year 11 as degrees, and it teaches it in Year 12 as radians. Both the methods that are taught in Year 11 and Year 12 require the unit circle to be used and manipulated using fractions. Now, if your students are not real strong at adding fractions, this is a big problem. Okay, but don't be afraid to be brave and teach them something different. Okay, once they get the hang of it, what I've found is that they can go back and do the fractions. Isn't that odd? And I'll give you an example of that. So basically the rote part that I ask you to do is to consider an equilateral triangle, and the equilateral triangle has the same sides, they're all length 2, and that means that the internal angle is 180 degrees, so each angle is 60 degrees, or in exact values, trig speak, in terms of radians, the bigger angle has the smaller denominator. Now, why would I do that? Well, something that I don't want you to do rote, but I'm going to put it up anyway, is the unitary method. And you will hear about this. It crops up in year 8, I think. Now, the idea here is that there's 180 degrees in pi radians. So if I want to see what's in 1 degree, I would divide both sides by 180. Whoops. I would divide both sides by 180, and that would give me 1 degree is equal to pi on 180. So that's the unitary part. Goodness gracious. So that's the part that says, okay, so if I've got 1 degree, how do I get 60 degrees? Well, you just multiply by 60 both sides. You take your unitary equivalent and you multiply by 60. So that will cancel. So 60 degrees will be equal to 6 goes into itself once and 18 3 times, pi on 3. Now you can do that for all of your, and they do teach it, and they generate tables and, you know, wonderful things. Couldn't care less. Hate it. Absolutely hate it. Do this. Okay, get used to doing this one. So what we're going to do is bisect this triangle. And remember, these are called know-how sessions, right? Not teaching scientifically. So this is what you can do when you're on your own and the textbook's missing. So what I've done here is I've got my 2. Now if that's 2 and it's bisected, that length there is 1 and that length there is 1, and that height there is unknown. And I might just call it something else. So I'm just going to draw the 1/2 with 2, 1 and x. Now that one's still 60 degrees, and this will be the last time I write the degrees. The bigger angle has the smaller denominator. The smaller angle has the bigger denominator. So we're nearly there. Hard to believe, but I want to find out x. So what we've got to do is come away and somehow understand that the hypotenuse square is going to be equal to the lower side square and the upper side square added together. So if this one up here is length of side 2, and this one here is length of side 1, and this side here is length of side x, then the two siblings will have the same area as their brother or their sister, whoever's got the bigger paddock, and we need to write that out. So the area of the siblings, the bigger siblings' privileged siblings paddock is 2 squared, and it's equal to our siblings paddocks of 1 squared plus x squared. So I'm going to leave the squares on at the moment because it's a concept. So I want to isolate the x squared term. So I'm going to undo and leave the squares. And then I'm going to rewrite it around the other way. And it's not until I get to this point that I'll take the numbers down. So x squared is equal to 4 minus 1. X squared is equal to 3. So x is going to be the square root of both sides, the square root of 3. Now we could do plus or minus, but we've only got a positive 1. So we've got x is equal to root 3. So we take that back up. Now, I know a lot of students who can't do that. To me, that's an example of a conceptual idea, because some teachers would jump from the diagram down here, or down to a number line here, x squared equals 3, and expect the students to cognate all of these lines by themselves. And I'm not sure that's fair. Eventually it'll be fair, but initially they need it. Okay? So, in my opinion, all of this stuff's my opinion, by the way, guys. I'm not preaching to you. If you think better or differently, that's okay. So what that means is your triangle now looks like this. And that's what I need you to be able to get to. I need you to be able to get to that with one more step. We're going to divide the sides by 2. And so I'm just cordoning it off because of all the noise in the adjacent column. But look at the proportions here. I'm deliberately doing the proportions. The smaller angle has the bigger diameter. The larger angle has the smaller denominator. 2 over 2, root 3 over 2, 1 over 2. So in actual fact, the one that we want, and this is completely unnecessary in some people's viewing, is to get to this one, which is our unit circle triangle. So I need you to be able to get to this guy here. Okay? Using these skills to build it up. And you might have a photographic memory and just go boop, boop, boop. My feeling is if you're going to teach it, you'll think, why don't I just teach the tables? Because there's something that you developed here that helps you remember where these numbers come from. A table doesn't teach you where the numbers come from. A memory table doesn't do that. Building these things up is a bit like building something up from first principles when you're doing proofs and limits and things, in my opinion. So this is very helpful from a memory aid point of view. The other thing that we want is the 45 degree version. Now the 45 degree version will have the same length on either side. The angle is pi on 4 because they're the same length, and the side is 1 on root 2. And I don't do that with the triangles, the proof for that one. Okay, I just expect you to take that. Alright, now why is this important? Because I want you to be able to recognize the smaller angle. Remember, we're doing exact values trig, so we're not just making up any old triangles. These are these triangles. Okay, so the larger angle, the smaller angle. What about if it's this way? Which one's the larger angle and which one's the smaller angle? What about if it's this way? Which one's the larger angle and which one's the smaller angle? What about if it's this way? Which one's the larger angle? Which one's the smaller angle? Not only am I asking you to tell me the angles, but I'm asking you to tell me the sides, because we're assuming that these are exact values trigs. So the short side's a half, the longer side's root 3 on 2, hypotenuse is 1. Okay, just by doing your development. Okay, smaller angle has the bigger denominator. Larger angle has the smaller denominator. So being able to build the map up of that triangle there is a big deal. That's the map building exercise. For this guy here, it's the same kind of thing, but it's a little bit cheekier in that they're the same. So if it's oriented around different ways, it's not such a big deal. Okay? But what I'm asking you to do is identify the proportions and to identify the size of the angles by sight. Okay? By sight. So if you've ever worked with a 4-unit student who can do the trigonometry, this is what they've learned. This is what they evolved to. Now they might not learn it this way, but they evolved to the recognition by sight. So there's a couple more things that I need to add before I can claim that we're exactly ready for exact values trig. One of the things that we'll need to add is the idea of an association. I've talked about proportion by sight. Okay, proportion by sight. The association, what are we talking about? Well, on a typical Cartesian coordinate system, that would be reasonable, wouldn't it? If I have an angle theta in there, and yes, I know we don't really want to do it, but I'm putting it up anyway. Let's do the sine of the angle. The sine is opposite over hypotenuse. The opposite over hypotenuse, y over 1. Now, do we normally write the number 7 as 7 over 1? No, we don't really, do we? We just know it's 7. We know it means that there's a 1 there, but we just write it as 7. What about if I do that? Maybe I could just do it this way. Ah. What's another name for y? What's another name for y? Another name for y is sine theta. Really? We just did it. On a unit circle, we can make this association. Let's do cos. Cos theta is adjacent over hypotenuse. Again, do we normally write that? No. What I'm teaching you is an association. What's another name for cos? Dun, 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 dun. Okay, this is big. This is the most important thing I can teach a student at university. Ian Learn and all that was fun, but this is big. What's Pythagoras? 1 squared x squared plus y squared. What's another name for x?
Cos.
What's another name for y?
Sine.
Ah. Is that where you came from? Okay. Now what we can do is we can be cheeky. A long way, teacher. Isn't he boring? Now cos is sec. Cos over cos is 1. Look at what we're doing. We're manipulating algebra. Sine is y. Y over x is... Oh, by the way, y over... I'm going to do this to you. Y over x is rise over run. Oh, really? That's y squared over x squared, so I should square them. Look, there's another one. Really? So let's do divide by sine squared. So that's cosec squared. Now that's not y over x, it's x over y. So what's the upside down of tan? Cotangent. And sine is 1. So there we've got another set. Okay? So these are the kinds of things that you'll need going forward. Okay? You can read a textbook or you can write this stuff out yourself, which I really encourage you to do. So from here down tonight, I encourage you to get some blank paper and do this 10 times over the coming weeks, months, whatever, just until you're comfortable with it. Okay? Now we've got a couple of ideas that I've used: proportion, association, and the final one is plus minus. So we're ready to do some three unit maths. So if we've got association, we've got proportion, and we've got plus minus, for want of a better turn of phrase. Okay, 4 theta is equal to find Okay, so this is very much a typical 3-unit question. Okay, we give students, this is in my test that comes in at uni, a question just like this, and they can't do it. And they can't do it because they haven't put all the bits together. Now I don't care if you teach all stations to Cronulla. You can do that. Or all stations to Central. Beg your pardon, that's the hypocrite and the bigot coming out in me. Now I just gave something away, didn't I? So you can do all stations to Central, and that's fine. But for you, as the practitioner, you need a backup, because all stations is sometimes very, very confusing, and this is your backup. Alright, when I look at sine and cos, I have to use these now: association, proportion, plus or minus. What does that conjure up? Yx large, small, plus, minus. Yx large, small, plus, minus. Now I'm going to tell you this. There was one occasion about 6 years ago where I taught a student this who'd come in to do the testing and asked me, came and said, before I do the test, I want a taster or a short course in trigonometry. So I sat down with her like this, like I did this, and when we got to this point, she literally squealed so loud in my ear it nearly bust my eardrums, made me nearly fall off the chair, because she had struggled. She went to a really well-to-do school, Meridian or one of those places, and it was like, oh my goodness gracious me. The kids struggle with it. So if you're struggling with it, it's okay. Alright, so x, y, larger, smaller, plus, minus. X, y, larger, you can write that down. X, y, larger, smaller, plus, minus. Which is which? What do we have? It's hard, isn't it? The proportion. We're trying to guess this theta. Literally, I've used the word guess. We're trying to see it. using the force. Use the force, Luke. Tell me theta. Okay, what is theta? Well, we've got x and y. We've got a large negative x and a small positive y. Does that fit? Root 3 on 2 is bigger than 0.5. So we've got a small positive y and a large negative x. Okay, so in your thinking bubble, by sight and recognition, you're wondering how 4 units do it, just do it. So we've got a small positive y and a large negative x. So we go to our unit circle, we go to the center, and we always do x first. Now which way is x? To the left or to the right? Which way? It's to the left, negative, isn't it? Long or small? Long. So that's that one. Then we go to the tip of the x and we draw a y, up or down? Small positive y. Okay. What's the angle theta in there? That theta is what? The smaller angle. So the smaller angle has the larger denominator. Now I've left a gap. Why have I done that? Because this is a 30-60 triangle. 30, 60, 90, pi, 3 lots of pi on 2, and 2 pi. 30, 60, 90. Okay, so yes, the base triangle is a 30-60 with proportions of a half and root 3 on 2. There it is. That's that triangle hidden in this problem. Okay, so how many? So it's a pi on 6, but it's a version of a pi on 6. 30, 60, 90, 120, 150. So we're going to count with me together. Just humour me. 1, 2, 3, 4, 5. 5 lots of pi on 6. Now could you do me a favour? Could you just run that through this? Sine 5 pi on 6. Cos 5 pi on 6. And tell me if I'm right or wrong. You'll have to be in radians. Sine 5 pi on 6 is? Makes me think I did something wrong. Going to radians.
They're
5.
correct for both of them. I just checked it.
Thank you. Dun, 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 dun. So the question becomes, I didn't use any adding fractions. I counted, which students can do, and I got the answer right. This method is bulletproof. It works. Okay? Now, whether you teach it to your students or not, I couldn't care less. Your head teacher might not let you. This is about empowering you. Okay? So the first year uni students I teach, they get the same thing. And they look at me with the same looks you're looking at now. It's like, what? Okay? Let's do another one. Now, what is it about this rotation? Well, if I take the unit circle, which is 0, pi, 180, 90, 270, 3 lots of pi on 2, and I put in a 30-degree triangle, it'll sit there like that. And it can also sit there. And you know the proportions now. You know the positives and minuses. And it can sit there. And it can sit there. Okay? If that's the 30 degree one. And so it's got 30, 60, 30, come on, get it right, mate. 30, 60, 90, 120. So all you do is you count around. And in this particular example, it's got all of them. So if it was this one, my theta would be pi on 6, but it would be 1, 2, 3, 4, 5, 6, 7 lots of pi on 6. That angle there is 7 lots of pi on 6. Okay? This one here is 11 lots of pi on 6. It just works. It just works. Okay? If I have my triangle the other way, still so many problems are taught through this lens. I'm not wasting your time, folks. I'm not wasting your time. So many problems. This angle here now, theta, is what? The bigger angle. It's got the smaller denominator. 1, no, that's 90. That's no good. 2, yes. 3, yes. 4, no. 5. So all of them can be covered in 5 counts. So this angle here is 5 lots of pi on 3. Okay? It's just counting. You just count. It's not hard. And if you can do that, and for the 45 degree ones, same thing. Now these are the 1 on root 2s. They were the root 3 on 2s and the halves. These are the 1 on root 2s. 45 degrees, 90. So we can count 90 plus 45, 135, 180, and so on and so forth. So they will count. So that angle theta is equal to pi on 4. This one here is equal to 1, 2, 3, 4, 5 lots of pi on 4. Now I'm being very specific about this pi on 4. Okay, so they're the 3 specific cases that you must know, and that's how you manipulate them using this counting method. Okay, so we'll do another quick one just by way of example. I'll forego all the and I'll do sine theta equals minus 1 on root 2, cos theta equals 1 on root 2. Okay, proportion, association, plus minus. Are they bigger, smaller, or the same? Bigger, smaller, or the same? They are the same. X and Y are the same. So what's the angle? What's the base angle? Just off the top of your head, if it's a base angle, what is it?
45 degrees. You
just looked at it and saw it. Bingo. So when you're sitting down with a 4-unit kid and they do it, you know what they just did. They recognised it. Okay? So if it's 45 degrees, all we need to now know is work out which 45 degrees. Thank you very much. So there's our first one. So we start in the middle, which are a positive cos, positive x, and a negative y. So it turns out we're going to have to do a bit of counting. Alright, you ready? 1, 2, 3, 4, 5, 6, 7. So that angle there, I should have stopped it there. That angle there is 7 lots of pi on 4. You can check that with your calculator. It's easy, it's bulletproof. There's no adding pi, subtracting pi. You know what the beauty of it is? You know what I love about this method the most? Negative angles. It's awesome. Positive angles you count that way. Negative angles you count this way. Look at this. Theta is 1. Theta is negative pi on 6. Guess what that's equivalent to? Positive 11 pi on 6. Count. 1, 2, 3, 4, 5. The negative angle is negative 5 pi on 6. Guess what its equivalent is? Plus 7 pi on 6. If you get to know this, it's no longer confusing. You teach negative angles using fractions. I dare you to 17-year-olds. They're going to start throwing things at you. And it won't be compliments. If they learn how to do this, it's dead easy. The reason I just threw that in is because you'll learn to recognise it. As things come up, you'll see it and you'll go, ah, I know what that is. That's a negative angle. It's not such a big deal. Alright, so here's a kind of off-the-cuff angle. One more association thing I'll do. In all of these unit circles with their hypotenuse of 1, we can think about x and y. Y is small, x is large. 45 degrees, y got bigger, x got smaller. 60 degrees, y got a lot bigger, x got smaller. Now if I come to the axis, if you think about the limit idea, that's an invisible triangle, but we know that x was diminishing and y was getting bigger. So y here is equal to 1. What's x equal to? What's the width of x equal to? We saw it diminishing. It's going to get to 0. And then as we build we move on, x is getting bigger, y is getting smaller. X is getting longer, y is getting smaller. X is getting longer, y is getting smaller. What happens here?
Y goes to 0.
Y goes to 0. And guess where that is? And x is negative 1. It just works. And the diminishing triangles, what happens here? Zero. X is getting bigger, 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 until eventually we get to here. At 0 or 2 pi, or whatever you want to call it, x is 1 and y equals 0. But when we say x and y, what do we mean? We mean sine and cos. So this is a question I put in the testing thing that I put up. And I deliberately obfuscate What's the obfuscation? I can't even say the word, I shouldn't try. The obfuscation is what? I've put the fraction together. So what's this question talking about? Cos means what? X. This question is saying what's the length of x at? Now, I should have written this if I was a nice person. What's the difference? 3 lots of pi on 2. This one's asking for x here. And that is? That is
0.
There you go. Okay, now let me tell you something. If you don't have this, these kinds of questions are very, very traumatic for students. 3-unit questions are very traumatic in trigonometry for this very reason of recognition. So anyway, that's my finish on that. It'll come up now, and when it does, it'll be more obvious to you where we're getting the numbers from. So if you start looking in your 4-unit stuff and you see solutions for theta, what's the difference between advanced Maths and Extension Maths Pro Numerals. Extension 2 will have a lot more trig in it, inculcated in every aspect of it. Alright, so I'm just going to press